Hey guys, this is Saptarshi here and welcome to our YouTube channel. So last video tutorial we have discussed about the problem of regularization and some useful techniques like early stopping, dropout and then regularizing the objective function. Okay, so today we are going to look at another important technique called as data augmentation. But before that, just to set the context that we discussed why regularization is required. Regularization is required for overfitting. Okay, so what is overfitting? Overfitting is a common problem in machine learning where the model does well or satisfactorily well on the training data but cannot replicate the performance in the testing set or the validation set. Okay, so why this happens? Because the models has a tendency to memorize. Okay, and we understood that regularization is a shield against this overfitting. Okay, and we also understood that there is a relationship between the overfitting and the number of parameters a model has. Okay, so it turned out that if a model has more parameters, it has a more tendency to memorize or follow the data closely, or a tendency to overfit. Okay, and actually there is a very succinct definition of overfitting from Dictionary of Statistics which highlights just this part, that an overfitted model is a statistical model that contains more parameters than can be justified by the data, right? So this is what we are trying to tell, that more parameters, it is more prone to overfitting, and as neural net has much more parameters, right? So it has a much more tendency to overfit than normal machine learning models. All right. So now looking at regularization, actually it can be divided into explicit regularization techniques and implicit regularization techniques. Okay. So explicit regularization techniques are very general and broad-based techniques. It doesn't consider the type of the data. It doesn't consider the type of the architecture that it has got. Okay. So whatever we were discussing earlier, right? Your dropout, your L1, L2 regularization, which results into decay of weights, or your early stopping. All this falls under explicit regularization. In implicit regularization, actually you try to leverage your knowledge about the network architecture or your knowledge about the data. So data augmentation actually falls under this implicit regularization technique. All right. So now let's understand data augmentation. So as we were discussing that, overfitting is that when we have more parameters than the data can justify. Okay. So for that we have studied different techniques. But what if we can increase the data commensurate to the number of parameters? Okay, so that is where data augmentation comes to play. One of the most common area where it is used is your computer vision problems, object recognition. Okay, it has also found application in problems like speech recognition. Okay, and it actually solves interesting problems as well. Let's understand this. So let's say in your data set you have a Ford car which has a this kind of orientation, and you have a Chevrolet car. So both are blue, both are hatchback cars. However, the orientation is different. This is in training set. Now assume that, so this is a Ford car, this is a Chevrolet car. Now assume that you have a Ford car with the orientation of the Chevrolet in the testing set. Okay, so your model can identify the Ford car as a Chevrolet car because it may be overfitted to the color and the orientation of the car, right? So to solve this kind of problem, especially in case of images, we have a lot of operators available, okay, which are also called as transformations. So one such transformation is called as rotation transformation. So this is the original image, and rest of the three images that you see over here are rotated by certain angles. Okay, you can also crop. So you magnify the image and you only focus on certain part. Okay, so you can see that this is the original image, and this has been cropped over here like this. All right, and these are of course not the only two transformations that you can apply. You can also apply flip and scale transformation. Okay, and however there is something to be cautioned about. So maybe you are doing a character recognition problem, okay, small letters, and in the your original training was about B, and what you did is you actually generate something like a D, okay, by flipping, all right, by rotation. And similarly that can happen even for digits when you have 6 and 9. Okay, so this is a problem, you know, we should actually try to avoid. So it's important that we don't apply these data augmentations blindly. Another important problem is that we can generate scenarios which are completely irrelevant, right? So maybe, you know, you are trying to recognize objects, okay, from you know, from a car manufacturer's point of view, right? So you are trying to probably measure or count how many cars are being produced, right? And what can happen is that because of this rotation and transformation that you applied, you have an image of an inverted car, which is not at all going to happen, right? So these are irrelevant trainings that you are subjecting your network to. So this is also not a very good scenario, right? Okay, so now let's look at some other terminologies. So one terminology of augmentation is called as light augmentation. So light augmentation, okay, so you know, there are some good references over here. So it only does some amount of transformations like horizontal flips and horizontal and vertical translation, and only certain percentage of the images, right? So not all images it applies that. And then you can have heavier augmentation, where of course you apply more type of transformation like scaling, rotation, shear, etc. Okay, and you can also, and you also do contrast and brightness adjustment, right? So these are, you know, two different techniques. So this is a very interesting and nice reference over here. You can look at this. There is a lot of interesting studies they have done on both ImageNet and Cipher dataset on different type of image architectures or computer vision network architectures. Okay, all right. So here is a comparison. Here is a comparison when we are not applying any explicit regularizers. So we are applying only augmentations like light and heavy. And here is where we are applying some regularizers. So it is weight decay and dropout. So weight decay, you know, are the L1, L2 regularizers, and dropout also, you know, where you by some percentage or by some probability you off some neurons. So or and it has an effect like an ensembling of a model, right? Okay, so if you look at the result, all right, so this figure is the mean improvement from the baseline model, and this is the standard deviation, right? So based on different training sets and testing set combinations. Okay, so you see that using your lighter and heavier augmentation, you are increasing the classification accuracy by 9%. Okay, whereas if you use weight decay and dropout, the percentage is around, you know, 2.88, even with light and heavy augmentation applied. Okay, so this actually tells that how, you know, if you consider the network architecture and the type of data you are dealing with, how that can help regularize and improve the accuracy of your network. Okay, so you know, we covered data augmentation as the last regularization technique that we wanted to cover. And thanks guys for watching this video. Please give your comments, like and subscribe if you find this helpful. Thanks once again guys.